I would like to solve a question related to population proportion and their confidence intervals. This is going to be an additional question. I was planning to give this question as a kind of virtual quiz that you could work on your own, but I think that this is I think easier for you to watch the whole thing, and with respect to seeing the whole thing on a paper or on a PDF file. Anyway, I tried to come up with this question so that it's going to be pretty much contemporary issue. So the question is something like this. I'm not going to write the whole question. It's going to be a little boring for me to put it into the correct phrasing, but let's say that we have a vaccine and we have a placebo. Actually, this question will be slightly also be related with chapter 10, I guess, but you do not need to know anything additional related to chapter 10 or anything like that. So with your current info on statistics, you should be able to solve this. Anyway, we give, let's say 1,000 people, the vaccine to 1,000 people, and out of these 1,000 people, let's say that I'm just making up these numbers so that it suits the question. So let's say that there's a certain disease and 20 of these people get infected with this disease, whereas the rest of them do not get infected. And for the placebo case, let's make it simple. We again give this to 1,000 people. Note that it's not going to make any difference whether we change this number or not. And out of these 1,000 people, let's say that 80 people got infected with this disease. So the question consists of two parts. First of all, there are two separate questions. For those two questions, for those two cases, for the so vaccine and placebo cases, determine the point estimate of proportion of people being infected in the population, or the probability of being infected, and determine their confidence intervals separately. This is the first part of the question. So it consists of two independent parts. Then I'm going to try to combine these two. So this is going to be slightly different. Well, it will be pretty much different in a way from what is discussed nowadays. So it's just, there's going to be distinction as you are, I'll try to emphasize later. Anyway, let's just go with me and see what's going on. So for the vaccine case, so the question is, find this P1. Let's determine what this P1 is of all vaccinated people in the population. Note that this hasn't occurred yet. This is going to happen in the future, right? So this is a hypothetical case, right? I'm not talking about this sample here. Proportion of people infected, or probability. And P2 is going to be related with this placebo thing here. Actually, the reason why we give placebo is so that it's going to correspond to no effect case. So this means of all non-vaccinated people in the population, proportion of the people infected. So again, we do not probably know. Well, actually, this is probably what's going on nowadays. Actually, if you take a random sample, right, out of all these people, this ratio that we obtain actually should be identical within the sampling error limits, or confidence limits should be identical to the probability of the whole that we are going to observe to the whole population. So this, for instance, 0.08 or 8% here may be taken as a point estimate of the spread of the disease in the population nowadays. This can be used as a point estimate if this is a random sample, given that it's a random sample. However, usually in vaccine trials, it's not a random sample. usually the lower age group is excluded, and also older age group is excluded, or the possible side effects, things like that, which I'm not going to consider. All right, so the first question is give a point estimate of P1 and P2, and also give confidence limits for P1 and confidence limits for P2. Two totally separate questions. So first, let's try to solve this part. So point estimate, maximum likelihood estimator, if you remember, is actually, for this case, is basically x1 over n1, and it's the maximum likelihood estimator for binomial distribution. That was basically the quiz question, and as far as I read your quiz papers, there are few people who have managed to come up with the idea that it is binomial distribution. Most people have used geometric distribution or Bernoulli distribution. Not that binomial distribution, the number of successes compared to a train of Bernoulli trials, the number of successes are scattered in any order. So if you have, let's say, N1 of Bernoulli trials, and if you know where the successes are, then you can write them as P1 times P1 times 1 minus P1 times whatever in this case, right? So this is going to be success, failure kind of thing. But actually in the binomial distribution, you use and choose K here, which means those X successes may be scattered in any combination of these X values from N different trials. I think you get the idea. I'm not going to go into that. Maybe I'm going to do a separate video on quiz questions, which we have already solved actually in one of the office hours. Anyway, let me concentrate on this one. So for those who would like to solve this question, right, you may stop here and try to solve on your own and continue. All right. So actually I stopped as if it corresponds to your stopping the video. So here it is going to be actually equal to, if I can write this, over 1000, this is going to be 0.02, and P2 maximum likelihood estimate is going to be 80 over 1000, which is going to be 0.08. In other words, usually we would like to call these probabilities in percentage. I think it's easier for people to grasp the idea in terms of percentage. But note that they are point estimates, and they given some different 1000 people here for the vaccine and placebo trials, different number of x1 and x2 values could have come out. Therefore, different values of different estimates of P1 and P2 could have come out. So the confidence interval concepts deal with that sampling variance issue. So how do we deal with that? We should know the sampling distribution of P hat here. Sampling distribution of P hat, if you recall, under certain circumstances, and what are those certain circumstances? If n times P1 hat is greater than 5 and n times 1 minus P hat is greater than 5, in this case, you may use normal approximation. So, and Z is going to be our standard normal variable, which is going to be X minus, going to be N times P, which is the expected value of X, divided by N times P1 minus P. This is going to be standard normal distributed. We know that if these conditions are satisfied. Let's check these conditions for these two cases. For N1 and N2, actually this corresponds to X1 here. So it's going to be 20, and the other value is going to be 980. And for this case, it's going to be 80, and it's going to be 920, the other value. So both of these values exceed 5. Therefore, the Z statistic is going to be normal distributed. Actually, this statistic is going to be standard normal distributed. We prefer to use this form here, dividing both sides by n. Since I don't have the textbook with me right now, but I'm too lazy to take it out. So I'm just going to use this here, this derivation. You don't need to do this derivation again. You may just copy from your textbook. So this is going to be our normal distribution, standard normal distribution. This ratio is going to be, note that, p hat minus p, the true value, divided by p1 minus p over n square root. Here actually we use a trick. We give this to reduce the computations. We also use the point estimate here. The result is going to, the standard error will change very little whether we are going to be using p hat or p, if they are not drastically different from each other, and which we hope actually that there's not going to be a drastic difference. That's why actually we use a sample to estimate the true value. So this is going to be normal distributed. Therefore, it's going to be, this statistic itself is going to be between p hat minus 1 minus p hat divided by n minus z alpha over 2, z alpha over 2 is equal to 1 minus alpha. Now let's give a value for alpha. Usually it's going to be taken to be 0.05. Let's do the same thing, which is going to correspond to 95% confidence interval. And alpha over 2 is going to be 0.0225. That 0.025 is going to be somewhat very close to 2, which is going to be 1.96. So now let's finish the whole thing. Probability that our p-value is going to be this p hat minus z alpha over 2 square root of p hat. It's going to be multiplication here, minus 1 minus p hat divided by n p hat minus z alpha over 2 square root of p hat 1 minus p hat, and this is 1 alpha minus 1 minus alpha. Actually, as I said, you could have easily taken this equation from your textbook. And this values, now we are going to insert these values. Let's see what is our p. 0.02 is for the first p1. So this is going to be for the vaccine case. Minus 1.96 square root 0.02 times 0.98 divided by 1000. Now let me calculate this value here, just a minute. 1.96 times square root of 0.2 times 0.98 divided by 1000. 0.0087. Is that correct? I think, and I hope so. Yeah. And 0.02 plus 0.00. Is there another 0? Yes, another 0 is equal to 0.95. So for vaccine, the confidence interval is going to be 0.0112 and 0.13 and 0.0287 is the 95% confidence interval for P1. Note that this is P1, not P1 hat. That for vaccine. So in other words, let's put it this way. I think it's going to be easier to understand. Well, this is not the correct way of representing this. I guess P is going to be, when you write it that way, it's going to be, so between those two values, P1 is going to be with 95% probability. P1 is going to be between 1.13 and 2.87%, right? And the point estimate of P1 is found to be equal to 2.0% with that additional information. So note that there is hat here, there is no hat here. So this is the first statistics for the first case. So without vaccine, probability of 0.08. By the way, I just made up these numbers. It's not a video for pro-vaccine or against vaccine kind of thing. I just made up these numbers so that it's going to be interesting. 0.08, 0.92 over 1000 P2. Let's find this number. All right, this is 0.0 something. So I'm sorry. Okay, so the values that we find here, please check that it is the case. And 9.68%. The 95% confidence interval for P2, with P2 had 8.0%. So this is the result, which means that in our population, we have strong reason to believe that 6.3 to 9.68% of the population is now infected. If this is a random sample, the people who are using the placebo. And there is also, well, that's maybe a little bit of detail, but for the interested souls, especially, there are some studies which shows that the effect of placebo is also there is also the effect of placebo. So which means that since people, they do not know whether they are being vaccinated or they are given with placebo, but they still think that there is some possibility that there are vaccinating, it makes them better. That's the actually placebo effect. So that's another problem. So therefore, these values might be lower than if there is a psychological effect, which may be related to population, but that's all unrelated with what I'm trying to say for the time. Anyway, so for vaccine and without vaccine case. Now, this is the first part of the question, which is, I think, very straightforward, which you should be able to easily solve with your current knowledge. Now, the second part of the question is a little bit more interesting, and still you should be able to solve it. But as I said, it's a little bit interesting. Now, nowadays, the statistic that people are interested in is P1 over P2, or actually P2 over P1, 1 minus P2 over P1. That's exactly the statistics that people are interested in. Have I written it correctly? No, it is a little bit, I think it is incorrect. I correctly written it in the message over Moodle, which are written. Let me try to remember. I think it is 1 minus P1 over P2. Yeah. It is this statistic, which is efficiency, that people are interested here. So for this case, for instance, the point estimate of efficiency would be equal to 1 minus 0.02 over 0.08, 1 minus 2 over 8, 6 over 8, and whatever that 6 over 8 is. Is it 0.75? Yes. The point estimate of efficiency of the vaccine for this case is 0.75. Now, if you ask the question, what is the 95% confidence interval for the real efficiency, for this real ratio? This becomes a much more difficult question, which we are not, unfortunately, going to go into. So because the idea is the ratio, there are the ratio of the two binomial distributed random variables here. So this is a bit of a difficult derivation. So anyway, this is a bit complicated. So what we are going to do, we are going to try to solve a more easier version of that, but it's not as meaningful as efficiency. Still, it gives you an idea. I would like to see the difference between P1 and P2. I would like to find or estimate this difference. Call this D. What may this difference may correspond to? Since this is the one without vaccination and this is the one with the vaccination, probability of being infected with this disease. This is how much the vaccine decreases the probability of being infected. Still, this is not a very good a good metric actually. If it were people would be using this metric, still it's going to be applicable for our purposes. So I would like to give a point estimate for D, and I would like to determine a 95% confidence interval for D here. So what are those two? Where D is defined as the difference between those two probabilities. Well, D hat is very simple. Actually, D hat is going to be, well, actually, it's not that simple. Let's go step by step. Now, this is a population parameter. It consists of two other population parameters, but still this is a population parameter, which I do not know. So I should come up with a good estimate of this one. One thing that's straightforward in my mind is I'm going to use D hat as P2 hat minus P1 hat. Let's see whether I am justified in using this estimator. If I take the expected value of D hat, it's going to be equal to expected value of P2 minus expected value of P1, and it's going to be equal to P2 minus P1. Since I'm using maximum likelihood estimators here, their expected values are equal to P2 minus P1. Therefore, the expected value of D is equal to P2 minus P1, which is exactly equal to D. So it's a good thing that using D hat in this form, it may seem very obvious to you, but it is not actually. This seems to be a nice, at least in terms of unbiasedness, it seems to be a nice statistic. Well, the next thing is, if I'm going to use this one, I need to find variance of D hat. Let's do it. Now, since they are two independent populations, I can easily write it that way. Now, P2, what is it equal to? It is equal to X2 over N2. And P1 is X1 over N1. That's great. Now, variance of P2 is going to be equal to N2 is constant. X2 may change for different N2s. Therefore, it's going to be equal to 1 over N2 square variance of X2. X2 is binomial distributed, so it's going to be N2 times P2 times 1 minus P2 over N2 square. Very simply, this expression. Actually, we have already found this expression here. The very same expression that you see here. This is the variance of P hat. So needlessly, I derived this whole thing again. So actually, variance of P1 is going to be equal to P1 1 minus P1 over N1. Again, instead of these terms which I do not know, I'm going to replace them by their estimated values. So they are going to be approximately equal to P2 hat and P2, since they are not going to be that much be effective here. So variance of D hat is going to be equal to, let's see, P2 hat 1 minus P2 hat over N2 plus P1 hat 1 minus P1 hat over N1. Since N1 and N2 are both equal to each other, well, let's go to that step a bit later. So it's going to be easy to calculate. Let's N2 is equal to N1, which is equal to N, which is equal to 1000. So it's going to be equal to P2 minus 1 minus P2 plus P1 hat 1 minus P1 hat divided by N. Pretty much straightforward. Now I have the statistic also for D. Now what's going to be the distribution of D? Now since P2 hat and P1 hat, both of them are normal distributed, D hat will also be normal distributed. So D hat is going to be normal distributed with the expected value of what? The expected value of D hat is going to be equal to P1 minus P2, and the variance is going to be equal to variance D hat that we have found here. That's great. Now let's finish the question. So if D hat is distributed in this manner, right? Therefore, D hat minus P2 minus P1 is going to be standard normal distributed. Square root of variance of diet, I'm not going to write the whole thing again, is going to be standard normal distributed. Now, as you can see, this is a little different question from the previous one, but I make it similar to the, or I have that frame over that for the general population, proportional population cases, I make it fit to that form, I may say. So here when I, so probability that Z alpha over 2 minus that this thing alpha over 2 is 1 minus alpha, the very same probability here. So now let's finish the whole thing. Probability that I'm going to put this whole thing here, and I'm going to leave this P1 minus P2, which I call to be equal to D here actually, right? So the left-hand side is going to be D alpha over 2 times, now I'm going to write the whole variance thing, square root of P2, 1 minus P2, plus P1, 1 minus P1, divided by N is going to be equal to P2 minus P1, which is the quantity that I would like to determine, B hat plus Z alpha over 2, again, the same expression. I'm too lazy to write the whole thing, 1 minus alpha. So now let's finish the question. D alpha is found to be equal to, what was that value? It's the difference between P2 minus P1. Actually, I can even replace that one to make it look nicer, right? Instead of this one, write P2 minus P1 hat. P2 hat minus P1. Now, probable that P2 minus P2 hat minus 0.8, 0.2, I've forgotten the values. Is that so? Let me check. Point, actually, it's so, yeah, 0.2, 0.8. 0.6 minus 1.96 square root, oops, this whole thing 0.8 times, well, we have hat here everywhere, replace them, 0.08, I'm sorry, 0.92 plus 0.02, 0.98 divided by the single 1000. If N1 and N2 were different, then we would have two denominators here. That would not make anything different, right? We would have been using N2 and N1 here. Question wouldn't be any more difficult. Minus P2 minus P1. And let's now find this whole square root expression here. 1.96 times square root of 0.8 times 0.92 plus 0. Times 98 divided by 1000. All right, we have found this expression to be equal to another 0 here. .06, I'm sorry. 0.8 and 0.2, 0.6. So here the confidence interval will be 4.11%. Let's make it simple. 4.1% and 8.9%. So P2 minus P1 is going to lie within that interval at 95% confidence level. And the point estimate here between the probability of having been infected, the difference between them is 6%. Plus, please note that this is not the this is not the metric that we use. It's not the measure that we use. The reason is very simple. If you think about it, 6% of decrease of being infected with the disease, does not mean much. Actually, it pretty much underestimates the effect of vaccination, because from 80 people to 20 people, the number of infected people has decreased for over 1,000 people, but it says 6%. Why? Because actually it is the difference between the probabilities. So the ratio of these probabilities is a much, much more intuitive is and also informative matrix. That's why we use the efficiency statistics instead of this one. But I just wanted to give you a kind of general idea how to use the information that we have learned in this course, somewhat familiar with the real life events, I may say. The actual calculations are a little bit out of the scope of this course. But I think this gives you I hope this gives you a general idea.